1. Introduction and the asteroid threat. Asteroids and meteoroids pose a potential threat to Earth, ranging from minor local damage to global catastrophic events. Even relatively small space rocks, if they enter our atmosphere at high speeds, can release enormous amounts of energy, causing shockwaves, structural damage, and injuries. A recent example of this is the Chelyabinsk meteor that exploded over Russia in 2013, measuring about 20 meters in diameter. It released a blast, equivalent to hundreds of thousands of tons of TNT. Windows shattered, thousands of people were injured, and buildings were damaged across the city. The Chelyabinsk event demonstrates that even modest-sized asteroids can have significant consequences. The explosion in the atmosphere creates a bright flash visible over long distances, but the shockwave arrives seconds later, increasing the overall damage. This event also highlighted the difficulty in predicting asteroid impacts. While some near-Earth objects are tracked, others can approach undetected, revealing the limitations of our current monitoring systems. Understanding these threats is essential for preparedness and response planning. Studying asteroid risks is not just academic, it's about real-world safety. Scientists continually observe the sky, calculate orbits, and model potential impacts to protect communities worldwide from potential asteroid hazards. 2. Asteroids' formation and structure. Asteroids are remnants from the formation of the solar system. Around 4.5 billion years ago, rocks and dust coalesced to form protoplanets. Inside these bodies, heavy metals like iron, nickel, and iridium sank toward the core, while lighter silicate minerals remained near the surface. Some of these protoplanets grew into the planets we know today. However, many collided with each other and fragmented into smaller pieces. These fragments continued orbiting the Sun, colliding further and breaking into even smaller pieces, forming the asteroids we observe today. Asteroids have different structures depending on their origin. Some are loosely bound rubble piles, while others, composed mostly of metal, represent the cores of ancient protoplanets. These metallic asteroids are essentially the oldest materials in the solar system. Formed over 4.5 billion years ago, most asteroids orbit between Mars and Jupiter in the main asteroid belt. However, some stray closer to Earth. These near-Earth objects pose a direct threat, because their proximity makes collisions possible. Understanding their structure and composition is crucial for predicting potential impact effects and planning any necessary mitigation strategies. 3. Chelyabinsk and historical collisions. The Chelyabinsk meteor of 2013 demonstrated how even relatively small asteroids can cause massive damage. Traveling at high speed, it exploded about 30 kilometers above the ground, releasing energy brighter than the sun for a brief moment. However, the shockwave reached the surface after 90 seconds, causing most of the destruction. Windows shattered, thousands of people were injured by flying glass, and over 1,000 buildings were damaged. Videos captured locals watching the sky, initially amazed by the bright flash, only to be caught off guard by the destructive shockwave. This event also highlighted the challenges of predicting asteroid impacts. Scientists accurately predicted another near-Earth asteroid, Duende, 16 hours later, but the Chelyabinsk meteor went undetected. This shows that, even with advanced technology, identifying all potential threats before impact remains difficult. Since 1988, over 1,200 asteroids larger than 1 meter have hit Earth, yet only 5 were detected before impact, and those only on the day they struck. Despite numerous ground and space-based telescopes, many dangerous asteroids remain unnoticed until it's too late. Understanding these past events is vital. They remind us that asteroid impacts are not just hypothetical, they are real and ongoing threats to life and infrastructure on Earth. 4. Threatened regions and near observations. Most asteroids orbit safely within the main asteroid belt between Mars and Jupiter. However, some stray close to Earth. These are called near-Earth objects, NEOs. Their proximity makes them potentially dangerous, and monitoring them is a high priority for astronomers. Even when a near-Earth asteroid is detected, predicting its path is challenging. With only a few days of observation, calculating its future trajectory accurately is difficult. Gravitational effects from the Sun and other planets, as well as chaotic orbital dynamics, can shift its path over time. Currently, over 1 million asteroids have been identified and catalogued, but only around 24,000 are near-Earth objects. These require special attention, because even small miscalculations can lead to underestimated threats. Smaller asteroids, even those just a few hundred meters wide, can cause significant regional destruction. Large cities, industrial centers, and even entire countries could be affected depending on the impact location. This emphasizes the importance of continuous tracking, orbit analysis, and preparation for potential hazards. In summary, while the majority of asteroids remain far from Earth, the few that approach close enough pose real risks that demand vigilant observation and international cooperation. 5. Detection methods and challenges. Detecting asteroids remains challenging even with advanced technology. Most asteroids are small, dark, and difficult to see, making ground-based telescopes less effective. To overcome this, astronomers use multiple observation techniques to track these objects. A common method involves taking a series of photographs and looking for moving points of light. Stars and galaxies remain fixed, but asteroids slowly shift position. As they orbit the Sun, computers, and artificial intelligence analyze these movements to identify potential threats. However, not all asteroids can be observed. Those approaching from the direction of the Sun are nearly invisible to ground-based telescopes. Space-based telescopes and continuous scanning programs are essential to monitor these hidden dangers. The difficulty in detection is compounded by the complexity of asteroid orbits. Gravitational influences from planets can subtly alter trajectories, making long-term predictions uncertain. This chaotic nature limits our ability to forecast asteroid positions with complete accuracy. Even small asteroids, ranging from a few meters to several kilometers, can cause significant damage. Their dark surfaces reflect only a fraction of sunlight, so the best chance to spot them is when they are fully illuminated. Continuous observation and improved detection technology are key to mitigating potential threats. 6. Impact scenarios and damage potential. Asteroids can create a wide range of impact scenarios depending on their size, speed, and composition. Small asteroids usually burn up in the atmosphere, causing minimal damage, while larger ones can devastate cities or even entire regions. The energy released during an impact is tremendous. For example, the Chelyabinsk meteor, only about 20 meters wide, released energy equivalent to hundreds of thousands of tons of TNT. The blast produced a shockwave that shattered windows and caused thousands of injuries. Larger asteroids, several kilometers in diameter, can trigger global catastrophes. The Chelyabinsk impact, which led to the extinction of the dinosaurs, illustrates the scale of such events. Debris thrown into the atmosphere can block sunlight, causing climate shifts and ecological collapse. Impact effects also depend on location. A strike over the ocean could generate tsunamis, while land impacts may lead to fires and widespread destruction. Simulations help scientists predict these outcomes and prepare mitigation strategies. Understanding potential damage is crucial for early warning and planning. Even small asteroids can cause significant regional damage, and larger ones have the power to alter life on a global scale. Preparedness relies on observation, analysis, and international coordination. 7. Mitigation strategies and preventive measures. Scientists have proposed several strategies to reduce asteroid threats. One common idea is to use explosives to fragment a large asteroid. However, breaking it apart could create multiple dangerous fragments, still capable of hitting Earth. Another approach is to gently alter an asteroid's trajectory. By attaching a spacecraft and applying small forces over time, the asteroid can be nudged off a collision course. This method requires precise technology and long-term planning, as asteroids often rotate and have complex structures. Laser ablation is also considered, focusing lasers to heat the asteroid's surface and produce thrust. While theoretically possible, current technology cannot deliver sufficient energy from Earth to significantly shift an asteroid's path. Other ideas, like covering an asteroid with reflective materials to change its radiation absorption, face practical challenges. Deploying enough material and ensuring proper attachment is technologically difficult. Ultimately, prevention relies on early detection and long-term monitoring. The earlier a potential threat is identified, the more options are available. Concentrated global efforts, advanced observation, and targeted strategies are the best defenses against potential asteroid impacts. 8. Global cooperation and scientific efforts. Asteroid threats cannot be addressed by a single country. They require international cooperation. Countries share observational data and conduct joint research to develop strategies against potential impacts. Collaborative efforts improve both detection and preparedness. Scientists continuously monitor the sky with ground-based and space telescopes. This ongoing observation allows for the tracking of near-Earth objects and the calculation of their orbits. Still, some objects remain undetected, highlighting the need for more advanced technologies. Global cooperation extends to emergency planning. If an asteroid is predicted to impact a specific region, coordinated evacuation and disaster response plans can minimize casualties. Lessons from past disasters inform these strategies. Scientific research also focuses on understanding asteroid composition and behavior. This information is crucial for deciding which mitigation methods could be effective. Knowledge sharing ensures that responses are well-informed and timely. In conclusion, protecting Earth from asteroid threats requires a combination of global cooperation, continuous observation, and scientific research. International collaboration enhances preparedness and reduces the potential impact of asteroid hazards. 9. Future risks and awareness. In the future, Earth will continue to face potential asteroid threats. Large asteroids are rare, but small to medium-sized objects pose a more frequent risk. Continuous observation and risk assessment are essential to minimize damage. Scientists use historical data and simulations to identify high-risk areas and predict potential impacts. These predictions enable early planning, including evacuation strategies and emergency response measures. Public awareness is also crucial. Educating people about asteroid hazards reduces panic and promotes appropriate actions during emergencies. Schools, media, and outreach programs help inform communities about these risks. Advancements in technology improve detection and tracking. Space-based telescopes and artificial intelligence allow astronomers to identify potentially dangerous objects more quickly and accurately than ever before. In summary, mitigating future risks requires vigilant observation, public education, and advanced technology. Awareness and preparation ensure that humanity can respond effectively to asteroid threats and protect lives and infrastructure. 10. Conclusion and recommendations. Asteroids and meteoroids pose a potential threat to Earth. From local damage to global catastrophes, large asteroids are rare, but even medium-sized objects can devastate regions and disrupt lives. Understanding these threats is vital for preparedness. Scientists continually monitor the sky, calculate orbits, and simulate impacts to predict potential hazards. Early warning systems allow communities to prepare and evacuate if necessary. While intervention methods are limited, detection remains our most effective tool. Current technology cannot reliably deflect large asteroids, and even smaller objects pose significant risks. Therefore, prevention relies on continuous observation, precise orbit calculation, and global cooperation. Sharing data and research enhances our ability to respond effectively. Public education is another key component. Informed citizens are better prepared to follow safety instructions during emergencies. Outreach programs, media coverage, and educational initiatives increase awareness and resilience. In conclusion, humanity's best defense against asteroid threats is a combination of scientific observation, international collaboration, and public preparedness. By staying vigilant and informed, we can reduce the risks and safeguard our planet from potential asteroid impacts.